we've seen these before. A scatter diagram is known by many names, such as a scatter plot, scatter graph, or correlation chart. Usually you don't see it as correlation chart, but that's what it's showing you. This diagram is drawn with two variables. Usually the first variable is independent and the second variable is dependent. So usually we're going to have our independent variable is going to be our x-axis, and our dependent is going to be our y variable. It's going to be important for you to know that for the homework, because you have to figure out which is your x values and which are your y values in order to solve it. So you might have to think back on that. The easy one is time is almost always going to be your independent, unless you're dealing with very high physics level stuff. Otherwise, time is going to be your independent and everything else will become your dependent. All right, classifying relationships or lack thereof. Now, the reason why it's called a scatter diagram is because real-world data does not follow particular models. We can say it looks close to linear. It looks close to this line that it's following, but real-world data is not going to fit into a nice, neat little box. If I measure everyone's height in here, we're going to have stuff across the board. We can't say that every junior or every senior is going to be a specific height. However, if you put it on a scatter plot, you can kind of see a general pattern. As you get older, generally you get taller. So each class will be slightly taller, but it won't be exact. That's why we kind of have this scatter shot of all this stuff that doesn't perfectly line up, but it can give you an idea of whether there's a correlation between the stuff. So if a pattern appears in a scatter diagram, then there is a relationship between the variables. If the points on the scatter diagram look like they're scattered about a line, then we say the relationship is linear. We say it's a linear correlation. Otherwise, the relationship would be non-linear. So if we look at our three examples, it looks like nothing, there's no pattern developing. We have no idea where over here where our next point would be. It would just be, we have kind of a free-for-all. However, we look at this next one, we have this little linear relationship that if I drew a line through these, if I drew a line through those, it kind of goes through all of them. Then if I say, if I go way over here, about what value would that be? We could go straight up to the line and say, well, it's going to be about here. We have a pretty good idea because we have a nice little straight line. Our last one, for the sake of this class, we're going to call it a non-linear relationship. If you have taken a stats course or you've seen studies with this, you'd know that this is actually a quadratic. We have cubic, we have quartic, we have exponential relationships. They all follow the graphs they sound like. This would be a quadratic relationship because a quadratic would go through all of these points. However, for the sake of this class, we're not going super in-depth. We're just going to have three classes. No relationship, linear, basically other, non-linear. That's what it stands for. Those are the only three you need to know. There is a relationship, but it's not a straight line, so we're going to go with non-linear. So if we look at the examples down here, we're supposed to label the relationship for each of the scatter plots. That first one, it's just like buckshot. There's stuff all over the place. There's no line I can draw on it. There's no curved line I can draw on it. So that's going to be no relationship. No apparent relationship. Our next one, they follow a nice little line. Then if I threw a line through it, they all kind of go around that line. So that would definitely be a linear relationship. Although our next one is not linear, you can kind of picture a pattern developing that it goes up and then it comes down. So there is a relationship. It's just non-linear. So that would be a non-linear relationship. Just to speed things up, we're going to go ahead and say that the bottom one is also non-linear because it's almost the exact same shape. And these two would both be linear because we could draw a line through it. So all I'm expecting you to be able to recognize is no relationship, linear, and non-linear. The next thing we do have to know how to plot scatter plots from given data. We are given a whole set of data up here. We're given years, and we're given number of people in a labor workforce. So the table below shows the year and the number of persons in the labor force in the U.S. Big takeaway from this one is when we're talking about years like 1960, 1970, 1980, we don't actually put 1960, 1970, 1980 on our X, especially when we're using our calculators. Generally, we try to simplify it by, instead of 1960, we just cover up the 19 and say, well, 60. Basically 60s, 70s, 80s, 90s. The trouble always comes in when you get to the knots. That 2000 would then become 100. So you have to keep track of it there. All right, so it says make a scatter plot of the data. So we're going to go over at 1960. So that's going to be 60. And we're going to go up to 70. 60 and 70. Well, it goes from 80 to 100, 60, 80, and then 100. So between 60 and 80, right smack dab in the middle, would be our 70. So it'd be about, if it would let me draw instead of copy and paste. There we go. Then in 1970, we had 82, so that's going to be a little bit above 80. Maybe about there. 1980 is going to be 106. Maybe about there. In 1990, we're going to have 125. Maybe about there. And finally in 2000, which is 100 on my X, it'll be 141. Maybe about here. Then it says draw a line that appears to fit the data. So we're just going to draw a line through all of those points. I'm not looking for the perfect line. I'm just looking for one that generally looks like it's going through all of those points. Kind of like that. In stats, that is called the line of best fit. That is the line of best fit. So we can go ahead and label that as the line of best fit. I almost said fet. Let's go with fit. That is our line of best fit. We use that line to come up with points that are not on there, or to approximate values that aren't on there. We can extrapolate and we can interpolate. Interpolate means that we are going to take values that are between these 2 points. Extrapolate means we're going to take points that are outside of those 2 things. I'm not too worried about those words. It's just what they use for stats. So it says here, use your graph to estimate the number of persons in the labor force in 1985. Obviously, it's not a point they gave us, but based upon that line of best fit, we can go over to 1985 and just work our way up and guess at what point that's going to be. Well, it looks like it's slightly above halfway. So anything around maybe 115, 116, 117, 118, 119 might be pushing it. Anywhere between there would be a good guess. I'm trying to see what I had for the actual value. Keep it the same as the other class. We came up with 115 million for that one. All right, then it says use your graph to predict the number of persons in the labor force in 2010. Well, if this is 2000, then 110 would be our 2010. So I'm looking at that imaginary point way up there. Well, if that's 140, 150 would be halfway. This would be 160. So it's like 161, 162 or something like that. Depending on your line, you're going to have a slightly different answer. So we're going to say like 161 million. I'm not looking for perfect answers. If I put this on the test, depends on how you draw your line. Just don't do something crazy and say that's 140. Then you don't know how to read a graph. All right, but as long as it's close, if you're like, okay, it's somewhere above 160, then we're going to be okay. All right, that's drawing a scatter plot and putting a line on it and using that line to get data that wasn't originally given to us. The last thing I want to talk about is, depending on correlations, is how strong a correlation is. How strong a correlation is tells you how important the data you are giving or how much it actually matters to you. So for instance, all of these points follow a very strict line. So these guesses are probably pretty good, just based upon the fact that every one of these are following this nice straight line. However, if we look at this correlation right here that's 0.5, and I draw a line on it, and I make a guess somewhere on the line, I'm not 100% sure how close it is to the actual answer because it's pretty weakly correlated. The cause and effect aren't there. So it says the numbers between 1 and -1 are used to measure how strong a relationship is between two variables. 1 and -1 being the strongest, 0 being the weakest. Whether it's positive or negative just tells you which direction the line is leaning. So if we look at a +1, your variables are strongly linked together, just like this workforce one, that each year it seemed to rise at almost the exact same rate. That would be a 1, and it's a +1 because our slope is positive. A slightly weaker one would be 0.9. It's still positive, it's still going uphill. We could have 0.8, 0.7, 0.6. At 0.5, you're starting to get near that kind of, you're not certain. It looks like there's a pattern, but you're not certain at any point you pick out here will match the real world data. When you get down to 0, there's just no correlation whatsoever. There doesn't seem to be any kind of correlation between those two variables. When you start going to the negatives, we start getting a stronger correlation, even though we're in the negatives. Negative 0.5 just tells you your correlation is going downhill. When you get to -1, that is a very strong correlation. It's just going down instead of up. So the hard thing about our correlation coefficient is the fact that 1 and -1 are both the same amount of correlation strength. It's just one's going uphill, one's going downhill. The closer you get to 0, the weaker your relationship is between your variables. All right, the last thing we're going to do today is we're going to use our calculator to actually solve problems. We're going to use our calculator to solve problems. So if you have your calculator, which you should every day, let's go ahead and take it out. And we're going to go through these steps to learn how to graph and come up with an equation. You're going to need this for the homework. You can't do this by hand. All right, so we are going to do that accompanying problem right below that says the example. So let's read that first. So it says the accompanying table shows the number of earthquakes worldwide with magnitudes between 5.0 and 9.9. I didn't want to add a new slide. I just wanted to go over a slide. All right. Well, our years are going to be our independent variables. So those are going to be our x value. The number of earthquakes that result in that year are going to become our independent, or our dependent, which we're going to call our y. It'll be our x values and our y values. These are exactly what we're going to graph in our calculator. So let's go back up to how to graph stuff. If you look at that very top left thing, the most important button you're going to use on your calculator for statistics is your stat button. Let me get out of here. Nope, I didn't want to do that. And your stat button is right here. Statistics, stat button. Go ahead and hit that stat button. When you want to edit columns, you're going to go ahead and hit edit. If you move over really quick, that's going to be when you want to calculate important things about your statistics. Well, we haven't entered anything in, so we're going to go back here to edit. And under this edit, we're just going to hit enter. Now, we are just going to use two columns. One column is going to be for the years. One column is going to be for the vehicles that we have. We're going to use this as our x, and this is our y. So we're going to put all our years in here. However, read the directions carefully. If you read A, it says use linear regressions on your graphing calculator to find the regression equation. It says let x equal 0 correspond to 2000. That's why if you look in my column, I used 0 for year 2000. 2001 will be 1, 2, 3, 4, 5, 6. If you have stuff in your column, if you already have stuff in your column, what you're going to want to do is you're going to scroll up to where you're highlighting L1, and you're going to want to hit clear and enter, and you should have just blank stuff to put in. So what I want you to do right now, if you have your calculator, I want you to put all your x values in. So that's going to be 0, 1, 2, 3, 4, 5, and 6. And then in the next column, L2, you're going to put that 15, 18, 13, 85, 13, 61, and I'll do it with you. So we're about at the same place. Yeah. Cool. Don't know how you got rid of them. Good job. Let me clear it all. I'd have to look into that. But it's not.
The way I cleared each row was just like going up and down and really make clear.
No,
Mm-hmm.
it's not how you do it.
Yeah, it's gravity do it.
Hang on.
It doesn't work. I did it.
I think you do.
Brody, how do you do it?
Yeah, your brother did some weird stuff.
Zoom
Whoever did this.
9.
Let's see if this works.
Press zoom, and then press 9. Oh. Mine made a box.
Alright, here you have an L1 and
Wait,
L2.
Mine shows a blank graph.
Go to
Alright, so I have 3, 4, 5.
Jack. Go to second y equals. I don't know. Oh, were you trying to create this guy? Oh, I feel like you were just that.
Alright, right above y equals you have stat plots. So we're going to hit second stat plot. Make sure all those are off, but you're going to turn one on. So I'm going to go to the number 1. I'm going to go ahead and turn that on. For hope, if you don't have an L1 or an L2, and you're just typing into L3 and L4 or something like that, this is where you would change your X value would be L3. And if you look down here, all of your blue buttons are your L1, L2, L3. So if you wanted your X value to be L3, you would just hit second L3, and that would make you're going to pull your X values out of L3. Okay? But you should be an L1 and L2 right now. We'll see if it works. All right, then you're going to go ahead and hit graph. And for most years, it won't show up right away. So you're going to go ahead and hit zoom. And whenever you're doing stats, it's going to be zoom 9, but you can also scroll all the way down to get to zoom stat. It will put all your stats front and center, and it will look just like that. All right, what we're going to do now, and what's most important, is it said you're supposed to use your linear regression on your graphing calculator to find the regression equation. Does everyone have these points showing up? Not yet. Did yours work?
Yes.
Okay.
I got it.
We're on Jack. Right here.
Use your calculator.
Yes.
And we're going to turn that on.
Second stack.
Now we're going to go to our graph,
No, second stack.
and we hit zoom. We either scroll up or down until we get to zoom stats.
Go down around.
Oh,
Good. Now
yeah, you have to get to 9. There it is.
now go to
Yep,
second.
right there. Or you can type in 9 if you don't, but most people don't memorize it.
What did you put?
Who else had
Oh
problems?
wait, now do, hold on.
Go ahead and graph. Is it not graphing?
Oh, graph.
Now hit zoom and scroll all the way down to 9. There you go. Okay. All right, yours should look like mine if you put all the stuff in. All right, now we're going to talk about our linear regression line. The first thing we're going to do is we're actually come up with the linear equation, and then we're going to go ahead and put the graph on top of this graph. All right, the first thing we're going to do is we're going to go ahead and hit second quit. Maybe I'll just go to mode instead. Second quit. Now we're going to go back to our stats. This edits our columns. This is any calculation I want to do. Well, linear regression is definitely a calculation. So we're going to go over to calculate. And you're going to scroll down to the one that says linear regression, AX plus B. Some of yours are going to have a whole bunch of linear regressions. You're looking for the one that just says lin reg AX plus B. Some of yours will, when you hit enter, will come up like this. Some of yours will ask for more information, like which columns you're pulling from. Make sure it says L1 and L2 for those that have it. For those that have that extra list, you have to then scroll down all the way to calculate. For anyone that has a calculator like mine, you're just going to go ahead and hit enter, and it's going to come up with your linear regression equation right here.
Wait, can you repeat that?
Yeah. So you're going to go to your stats button. Then you're going to scroll to calculate.
Yeah.
And you're just going to scroll all the way down to linear regression.
Yeah.
Then you're going to go ahead and hit enter. For some of yours, it'll come up on the home screen. For other people, it's going to come up with other information. Okay, then hit enter.
Oh, okay.
There you go. Yeah.
I only get the A. I don't have the R.
Okay, we'll go over that.
Okay.
I think I did a thing I couldn't done.
Yeah, no, you're fine. You're good.
Done.
What other stuff? Derek, look at it. You have to do all of this.
All right, who didn't get all that R and R squared stuff?
I did not get a mark.
Okay, we'll talk about why, and that's what that highlighted box is right above it. Some calculators just come when you reset it. It will go back to this mode where it won't actually show these. So if you look at that top right box, it says you just have to do it once, because you only have to do this once until you reset your calculator or something like that. So let's go to that top box. That says enable correlation coefficient. So what you're going to do first, I'm going to back out of here. You're going to go ahead and hit second 0, which will get you to your catalog. It says catalog on there. Then you're going to find your D button, which is your X inverse button. If you just hit the X inverse button, no other button, it will bring you down to your Ds. Then you're going to go all the way down till you get to diagnostic, and you're going to turn your diagnostic on. So you're going to get all the way to this diagnostic on, and you're going to hit enter twice. Enter will just put it on your home screen. Entering again will turn it on. Did everyone find that diagnostic on? Okay. Now you should be able to do your linear regression, and you should have your R and R squared values. Did that fix your R values? Yep. All right, so now we have a linear equation where A is our slope, and that B is your y-intercept. So we're going to go ahead and go back to our first problem. It says write your linear regression line here. So we're going to put y equals 117.4x plus 1269.1. I also do want to note really quick on your calculator, we did turn that diagnostic on. We're not going to do a whole bunch with it, but I did want to point out the fact that your R value for this one is 0.8. That's a mediocrely strong correlation. 1 is your strongest, 0.8 says, hey, most of the points are on that line. And if you look at your graph, we can kind of picture a line through it. And rather than picturing a line through it, let's go ahead and put the line through it. So to put our line through it, we're just going to go to our y equals because we're going to put a line on there. And if you look at this, we have a graph of regression line on here. Make sure your y is cleared. Then you're going to go ahead and hit your vars. Yeah, we're not going to do too much with this. You're going to hit your vars button, which is right here. Then you're going to scroll down to your statistics. And I'm going to go ahead and hit enter. And then we're going to scroll over 2 places, 1, 2, to our equations. And we're going to click on our regression equation. And that should put our 117.3928, all of those digits in there. Yes? That's because you didn't go to your function mode. Go to your mode and make sure it's in function mode. All right, this, you don't need to memorize how to do this. It just can make your life a lot easier on like an SAT or something like that, because this will give you exact values. Now if I go to graph, it's going to put the line right through those points. We don't have to guess. That is the exact line. All right, let's finish up the problem. The next question says, use the regression equation to predict the number of earthquakes in 2015. Note, in 2015, that means our x value is going to equal 15. So then we're just going to do y equals 117.4 times 15 plus 1,269.1. That's going to come out to about 30. But if you are someone that knows how to use your calculator, if you are someone that learned how to use your calculator and didn't just goof off the stuff we were doing, if you go back to your calculator and notice on your graph, there's a table button right above it. If you click on that table button, you can actually see all the values of x being plugged in. So if I had a whole bunch of problems, I say, what happened in 2050? What happened in 2049? What happened? You can just scroll to your indicated value. So in this case, we're looking for 2015. So if I just scroll down to an x value being 15,
How'd you get to this part?
it's right above your graph. You're going to hit second graph. And you're going to see that if you plug in 15, it is exactly 3030. You plugging in 15 gave you an approximation. This tells you it was exactly 3030. In 2016, you had about 3,147. In 2017, this is 3,264. So being able to put that in can save you some time if I have multiple problems rather than having to plug it in over and over and over again. All right, the last thing we are supposed to do, and this is where our whole statistics line of best fit breaks down. We are supposed to look at when there are no earthquakes. When are there no earthquakes? Does that make sense in the scale of things? No. No. We didn't have a period where we had 0 earthquakes per year. That's where it kind of breaks down. But they're asking for, where does y, because that's the number of earthquakes, equals 0? Where does y equal 0? So we plug that in our equation, and we have 117 point x, not point x, 0.4 times x, plus 1269. 0.1, and if you solve for x, you're going to come up with x being about -11. What does x being negative 11 mean in this problem? Yes?
It's 11 years before 2000, so 1989.
It'd be 1989. That's 11 years before 2000. So our answer would be 1989. Do you think we had 0 earthquakes in 1989 across the entire world? Definitely. In fact, if you look at even our calculator is disagreeing with our line too. Because if you look at, we have a point up here, we have a point down here, we have a point up here. It almost looks like we should have something that looks like that, where it's increasing, but it never reached a straight downhill. In fact, prior to 1989, according to our line, we had negative earthquakes. So in 1987, we had negative earthquakes. So that's where a linear regression breaks down. And it doesn't work all the way across our data, but in between, it should do a decent job of estimating stuff. All right, that is primarily what your homework is going to be. You're going to have several problems where you have to use your calculator to come up with a linear regression line. I do want to note, if you plug in 2000, 2001, 2002 instead of 0, 1, 2, 3, you will still get the correct answers, but you will have a different equation than I used. All right, my equations are based upon me putting 0, 1, 2, 3, and 4 in. So you might have a different equation, but you might get the same answers. All right, due to technical difficulties, we're running a bit behind, but do we have questions on the homework? Chris? 111? Okay. I would like to have more time to go over this, but we just don't, so I'm going to go ahead and take a picture of my answer key and talk about what was happening on there. So when we look at the picture of this, we were given a block and how far away that block was from a given wall. So because our block was 1 foot up and 5 feet away from the wall, what I'm actually going to do is I'm going to create an XY coordinate plane. I'm thinking of this as being my X, and this is my Y coordinate plane. Well, if that's the case, this block is negative 5 feet up 1 foot. So this point right here is the point negative 5, 1. Well, what I do know about a circle is it follows the equation x minus h squared plus y minus k squared equals r squared, where x and y are any points that are in the circle, and h and k are, in fact, the center of your circle. So when I come up with a point that's on my circle, negative 5 and 1, I can replace my x and y values with negative 5 and 1. Well, as it would stand, I would have, so if I just replace that x in there, I would have negative 5 minus h squared plus 1 minus k squared equals r squared. I can't solve. There's 3 variables. But if we look at how this circle is positioned, the center of this point, the center of any circle is exactly r distance away from any place on the circle. So if I look up here, my center of my circle is exactly r units away. And based upon my x going this way, it would be negative r units in that direction. Well, the height of it is going to be a positive r. So if I was going to do a point for this, I would call it negative r, positive r. Which means my x value of this is whatever my radius is, negative. And the y value of this is going to be whatever my r is, but that's positive. It's negative r, positive r. Then replacing my h with negative r, we're going to have negative 5 plus r. Then replacing my k with an r, we're going to have y minus r, or 1 minus r, which we have right here. As soon as you have that equation, you're pretty much done. You just have to square both of these and then solve for r using probably the Pythagorean theorem. No, I'd actually complete the square on that one because it's 1, and I would just have to use 12 divided by 2, so we'd have 6, and we could do that in our head, actually. Does that all make sense? Cool. Other questions? Yeah.
Number 113.
Number 113, we have a tortoise, and he's crossing a highway, and his speed is 2 feet per hour faster than normal. So when he's on the highway, he's going faster. If he can cross a 24 feet lanes in 24 minutes less time, then he can travel that same distance off highway. Then what is his normal speed? All right, so the distance is the same. It's 24 feet. Our rate on the highway is going to be faster. It's going to be faster by 2 feet per hour. And then our regular, so what I'm picturing in my head, I'm picturing distance equals rate times time, where my distance is 24 and 24. On highway, I'm doing x plus 2. Off highway, I'm doing just regular x. I'm going my regular speed. Then for time, I'm going to use, rather than coming up with a whole new variable for time, I'm going to say, you know what? Time just equals distance divided by rate. My thing is very, very slow. I should have taken this picture a while ago. There we go. All right, so we would have our time is 24 over x plus 2, and this can be 24 over x. Now, if our two times were the same, I could set them equal to each other, and I'd solve for x, and I'd be done. The times are not equal to each other. In fact, it says the highway, it takes them 24 minutes faster, which is actually 2/5 of an hour, because we're talking about, what are we talking about, feet per hour. All right, so since this one is faster, it takes him less time to cross the highway than it does regular. So I need to add time to the highway so that they're both equal to each other, right? Because if this is less time, I need to add to make them equal. So I added 2 over 5 to the highway time, and now that's going to equal as off-highway time, and now it's just solving for x. Other questions? That's it? Gracie.
How did you factor?
How did I factor 108? On number 108?
Yeah.
Did I factor it?
I don't know.
I-
It didn't show it.
Oh, okay. On 108, you couldn't factor it.
So how would you do it?
You'd probably put it in the quadratic formula,
Okay.
where you have 4, -50, and 74. I probably wouldn't complete this. I probably wouldn't complete the square because you'd divide everything by 4. And 4 doesn't quite go into 50 nice, so you'd be dealing with much harder. So I would definitely use the quadratic formula on that one. Other questions? Yeah, Leo.
107.
107. Oh, 107 is, we have a tennis court. It says that the area is 312 yards. So if the area is 112 yards, that means length times width has to equal 312. Well, we don't actually know the length, and we actually don't know the width. All we know is that the length is 2 yards longer than twice your width. So what you're going to have to do is what I did is I set my width equal to x. I let my L equal 2x plus 2, because it's 2 more than 2 times it. Then I set length times width equaling 312. I have no idea why I use W and X. All of those should be X's. That's just laziness. But those should all be X's. And we ended up with x squared plus x. You're going to end up with your width being 12. And your length is going to be 26. Now we just need to find corner to corner of it, which is just the Pythagorean theorem. Yep, 12 squared plus 26 squared equals x squared. Other questions? Okay. Unfortunately, we don't have a ton of time, but the rest of the time is yours. Do you have your homework?